Sedimentary structures. Objectives. The aim of this lesson is to understand an overview of all the sedimentary structures that are encountered in sedimentary rocks. The objectives of learning this module are to know about the following: identification of various structures on sedimentary rocks, mechanism of structures formed in sedimentary rocks, pre- and post-depositional process of sediments. After attending this module, the learner will be able to explain about the various types of sedimentary structures and their importance in stratigraphic construction and geologic interpretation. Sedimentary structures are the key elements for defining depositional environments, geological history, and surface processes. Introduction. Sedimentary structures are important attributes of sedimentary rocks. They occur on the upper and lower surfaces of beds as well as within beds. They can be used to deduce the processes and conditions of deposition, the directions of the currents which deposited the sediments as beds. Sedimentary rocks are characterized by certain unique structure and textures. The structures are megascopic and the textures may be microscopic. Sedimentary structures are classified into primary and secondary structures. Primary sedimentary structures are those that are formed at the time of the deposition. Secondary sedimentary structures are those that formed sometime after sedimentation. They result from essentially chemical processes, such as those which lead to the diagenetic formation of concretions. Primary sedimentary structures are divisible into inorganic structures and organic structures. Sedimentary structures are arbitrarily divided further into primary and secondary class. In this lesson, all types of sedimentary structures are highlighted. Primary structures. The first basic classification is related to inorganic megascopic primary sedimentary structures. Three main groups are defined based on their morphology and time of formation. They are PreDepositional structures, Depositional structures, and PostDepositional structures. The PreDepositional or interbed features are predominantly erosional. They include channels, sole marks, flute marks, groove marks. The Depositional intrabed features are predominantly depositional. They include massive flat bedding, including parting lineation, graded bedding, cross bedding, lamination, cross lamination. The post-depositional deform interbed and intrabed structures features are predominantly deformational. They include slump, slide, convolute lamination, convolute bedding, recumbent foresets, load structures. There are certain miscellaneous features like rain prints and shrinkage cracks. These are not belonging to the categories mentioned earlier. The first group of structures is PreDepositional with respect to the beds that immediately overlie them. These structures occur on surfaces between beds. Geopedants may prefer to term them interbed structures, though they were formed before the deposition of the overlying bed. This group of structures largely consists of erosional features such as scour and fill, flutes, and grooves. These are sometimes collectively called sole marks or bottom structures. The second group of structures is syn-depositional in time of origin. These are depositional bed forms like cross-lamination, cross-bedding, and flat bedding. To avoid a genetic connotation, this group may be collectively termed intrabed structures to distinguish them from pre-depositional interbed phenomena. The third group of structures is post-depositional in time of origin. These are deformational structures that disturb and disrupt pre- and syn-depositional inter- and intrabed structures. This third group of structures includes slumps and slides. PreDepositional sedimentary structures. The PreDepositional sedimentary structures occur on the intermediary surfaces between beds. They are formed before the deposition of the overlying bed. The majority of this group of structures are erosional in their origin. Channels. The largest pre-depositional interbed structures are channels. These may be kilometers wide and hundreds of meters deep. They occur in diverse environments ranging from subaerial alluvial plains to submarine continental margins. Channeling is initiated by localized linear erosion by fluid flow, aided by corrosive bed load. Channels are of great economic importance for several reasons. They can be petroleum reservoirs and aquifers. They can contain placer and replacement mineral ore bodies, and they can cut out coal seams. The fluvial channel filled with coarse sand, cutting down into finer sandstones and mud rocks are very unique structures in channels. Soil marks. Soil marks are erosional sedimentary structures on a bed surface that have been preserved by subsequent burial. These are of two kinds, as scour marks caused by erosive turbulence and tool marks caused by imprints of objects. Scour and fill. Smaller and less dramatic are the interbed structures termed scour and fill. These are small-scale channels whose dimensions are measured in decimeters rather than meters. They too occur in diverse environments. Tool marks. Tool marks are erosional bottom structures that can be attributed to moving clasts. These are erosional features cut in soft mud bottoms like flutes and grooves. They are, however, extremely irregular in shape, both in plan and cross-section, though they are roughly oriented parallel with the paleo current. In ideal circumstances, it has been possible to find the tool which cut these markings at their down current end. Flute marks. Flutes are heel-shaped hollows scoured into mud bottoms. Each hollow is generally infilled by sand, contiguous with the overlying bed, as shown in figure. The rounded part of the flute is at the up-current end. The flared endpoints are down-current. Flutes are about 1 to 5 centimeters wide and 5 to 20 centimeters long. Groove marks. The second important type of erosional interbed structure is groove marks. These, like flutes, tend to be cut into mud and overlain by sand. They are long, thin, straight erosional marks. They are seldom more than a few millimeters deep or wide, but they may continue uninterrupted for a meter or more. In cross-section, the grooves are angular or rounded. Grooves occur where sands overlie muds in diverse environmental settings. Syn-depositional or intrabed structures. Syn-depositional structures are those actually formed during sedimentation. They are, therefore, essentially constructional structures that are present within sedimentary beds. Bedding, stratification, or layering is probably the most fundamental and diagnostic feature of sedimentary rocks. Bedding is due to vertical differences in lithology, grain size, or more rarely, grain shape, packing, or orientation. A useful rule of thumb definition is that beds are distinguished from one another by lithological changes. Shale beds thus typically occur as thick, uninterrupted sequences. Sandstones and carbonates, though they may occur in thick sections, are generally divisible into beds by shale laminae. Sedimentary intrabed structures are of 5 categories. They are bedding and lamination, graded bedding, cross bedding, and cross lamination. An apparent absence of any form of sedimentary structure is found in various types of sedimentation unit. It is due to a variety of causes. First, a bed may be massive due to diagenesis. This is particularly characteristic of certain limestones and dolomites that have been extensively recrystallized. Secondary primary sedimentary structures may be completely destroyed in a bed by intensive organic burrowing. Bedding and lamination. The stratification of a sedimentary sequence is characterized by both bedding and lamination define stratification. Bedding is thicker than 1 centimeter, whereas lamination is thinner than 1 centimeter. Bedding is composed of beds. Lamination is composed of laminae. Parallel, also called planar or horizontal lamination, is a common internal structure of beds. The terminology of bed thickness varies based on the size of the beds. Very thickly bedded, medium bedded, thinly bedded, very thinly bedded, thickly laminated, thinly laminated. Beds also vary in their shape and definition so that planar, wavy, and curved types are recognized. And these may be parallel to each other, non-parallel, or discontinuous. Massive bedding. Genuine depositional massive bedding is often seen in fine-grained, low-energy environment deposits such as some claystones, marls, chalks, and calcilotites. Reef rock, biolithite, also commonly lacks bedding. In sandstones, massive bedding is rare. It is most frequently seen in very well sorted sands where sedimentary structures cannot be delineated by textural variations. Flat bedding. One of the simplest intrabed structures is flat or horizontal bedding. This, as its name implies, is bedding that parallels the major bedding surface. It is generally deposited horizontally. Flat bedding occurs in diverse sedimentary environments ranging from fluvial channels to beaches and delta fronts. It occurs in sand-grade sediment, both terrigenous and carbonate. This occurs under shooting flow or a transitional flow regime with a Froude number of approximately 1. Sand deposited under these conditions is arranged with the long axes of the grains parallel to the flow direction. Moderately well-indurated sandstones easily split along the flat bedding surfaces to reveal a preferred lineation or graining of the exposed layer. This feature is termed parting lineation. Graded bedding. A graded bed is one in which there is a vertical change in grain size. Normal grading is marked by an upward decrease in grain size. Reverse grading is where the bed coarsens upward. There are various other types. Graded bedding is produced as sediment settles out of suspension, normally during the waning phase of a turbidity flow. Though the lower part of a graded bed is normally massive, the upper part may exhibit the boomer sequence of sedimentary structures. Cross-bedding. Cross-bedding is one of the most common and most important of all sedimentary structures. It is ubiquitous in traction current deposits in diverse environments. Cross-bedding, as its name implies, consists of inclined dipping bedding bounded by subhorizontal surfaces. Each of these units is termed a set. Vertically contiguous sets are termed cossets. The inclined bedding is referred to as a foreset. Foreset may grade down with decreasing dip angle into a bottom set or toe set. Basically, two main types of cross bedding can be defined by the geometry of the foreset and their bounding surfaces: planar or tabular planar cross bedding and trough cross bedding. In tabular planar cross bedding, planar foreset are bounded above and below by subparallel subhorizontal set boundaries. In trough cross bedding, upward concave foreset lie within erosion scours which are elongated parallel to current flow, closed up current and truncated down current by further troughs. Cross bedding is commonly found in arenaceous sediments, oolitic limestone, and is some type of clastic limestone. Ripples and cross lamination. Ripples are a wavebed form that occurs in fine sands subjected to gentle traction currents. Migrating ripples deposit cross-laminated sediment. Individual exceed 2 to 3 centimeters in thickness in contrast to cross-bedding, which is normally greater than 50 centimeter thick. In cross-section, ripples are divisible into those with symmetric and those with asymmetric profiles. Symmetric ripples, also called oscillation or vortex ripples, are commonly produced in shallow water by the orbital motion of waves. In plan view, they are markedly subparallel, but occasionally bifurcate. Asymmetric ripples, by contrast to symmetric ones, show a clearly differentiated low-angle Stoss side and steep-angle lee side. Internally, they are cross-laminated, with the cross lamina concordant with the lee face. Asymmetric ripples are produced by unidirectional traction currents as, for example, in a river channel. The characteristic features of ripples depending upon current velocity, particle size, persistence of current direction, whether the fluid is air or water. Flacer, lenticular, and wavy beddings. Flacer bedding. Flacer bedding is where cross-laminated sand contains mud streaks, usually in the rippled troughs. These are commonly forms in relatively high-energy environments, sand flats. Wavy bedding. Wavy bedding is where thin ripple cross-laminated sandstones alternate with mudrock or commonly forms in environments that alternate frequently from higher to lower energies, mixed flats. Lenticular bedding. Lenticular bedding is where mud dominates and the cross-laminated sand occurs in lenses. They are commonly forms in relatively low energy environments. Reactivation surfaces. With some crossbed sets, careful observation will show that there are erosion surfaces within them cutting across the cross strata. These reactivation surfaces represent short-term changes in the flow conditions which caused modification to the shape of the bed form. Tidal cross-bedding. There are several features of cross-bedding which indicate deposition by tidal currents. Herringbone cross-bedding refers to bipolar cross-bedding, where cross-bed dips of adjacent sets are oriented in opposite directions. Herringbone cross-bedding is produced by reversals of the current, causing dunes and sand waves to change their direction of migration. Storm bedding, hummocky cross stratification HCS, swally cross stratification SCS. HCS and SCS are two particular types of cross stratification in sand grade sediment, widely thought to be the result of storm waves and deposition in the outer shore face and transition zone between fair weather wave base and storm wave base. Hummocky cross stratification HCS is characterized by a gently undulating low angle less than 10 to 15 degrees cross lamination with the convex upward part the hummock and concave downward part the swale. The spacing of the hummocks is several centimeters to 1 meter or more, and in plan view they have a domed shape. Gravity flow deposits, debris flow deposits. Debris flow deposits are typically poorly sorted, matrix-supported sediments with random classed orientation and no sedimentary structures. Thickness and grain size commonly remain unchanged in a proximal to distal direction. Turbidities. These deposits formed by turbidity currents are typically normally graded, ideally composed of 5 units, Boma sequence with divisions A to E, reflecting decreasing flow velocities and associated bed forms. Imbrication. Imbrication commonly occurs in water-lane gravels and conglomerates and is characterized by discoid, flat clasts consistently dipping upstream. Post-depositional sedimentary structures. The third main group of sedimentary structures is a result of deformation. These may be termed post-depositional because, obviously, they can only form after sediment has been laid down. The post-depositional deformational sedimentary structures are classified into various types based on the nature of deformation and sense of movement. They are nature of deformation, plastic, sediments lack shear strength, brittle, sedimentary possess shear strength. Sense of movement, dominantly vertical and dominantly horizontal. Vertical plastic deformational structures. Deformational structures that involve vertical plastic movement of sediment are of two main types. One group occurs within sand beds and may be loosely referred to as quicksand structures. Structures of the second group develop at the interfaces of sand overlying mud. A variety of structures develop where sands overlie muds. The mud-sand interface is often deformed in various ways. Most typically, irregular rounded balls of sand descend from the parent sandbed into the mud beneath. These structures are variously termed load casts, ball and pillow structures, etc. They are a variety of the broad group of structures termed sole markings or bottom structures. Load structure, load cast generation. Sole marking generally preserved on the lower side of the sand layer overlying the mud layer. often associated with turbidities, with a thin layer of coarser sediment on the top. Can also be defined as a bulbous depression formed on the base of a bed of sediment, developed by the differential sinking of the sediment while still soft into less dense sediment below. Dish structure. These consist of concave up laminae, generally a few centimeters across, which may be separated by structureless zones, the pillars. Dish structures and dish and pillar structures are formed by the lateral and upward passage of water through sediment. Dish structure is a particular variant of intra-sand deformation. This is seen where lamina or bedding planes are intermittently disrupted and upturned like the rim of a dish. Dish structure is a type of dewatering phenomenon that is particularly characteristic of fluidized sand beds. Ball and pillow structure. As a result of loading, a bed, usually of sand, can sink into an underlying mud and break up into discrete masses, forming the so-called ball and pillow structure. Convolute bedding. Quicksand structure involves the deformation of whole beds of sand up to a meter or more thick. It is loosely referred to as convolute bedding. On a smaller scale, laminated fine sands and silts also show penny-contemporaneous vertical deformation structures termed convolute lamination. This is similar in geometry to convolute bedding, but occurs in finer-grained sediment on a much smaller scale, generally in beds only a decimeter or so high. Recumbent foreset. These structures are caused by the vertical passage of water through loosely packed sand. This water may be due to a hydrostatic head of water, for example, as seen on an alluvial fan, example Williams, 1970. Alternatively, the water may be derived from the sediment itself. Sand will not compact significantly at the surface, but its grains may be caused to fall into a tighter packing. This results in a decrease in porosity. Convolute lamination. Laminated fine sands and silts also show penny-contemporaneous vertical deformation structures termed convolute lamination. This is similar in geometry to convolute bedding, but occurs in finer-grained sediment on a much smaller scale, generally in beds only a decimeter or so high. Convolute lamination is especially characteristic of turbidites, involving deformation of both the laminated and cross-laminated boma units. Horizontal deformational structures, slumps and slides. Slump structures, like the structures, involve the penny-contemporaneous plastic deformation of sand and mud. Slump folds, however, commonly show clear evidence of extensive lateral movement in a consistent direction. Slump folds are commonly associated with penny-contemporaneous faulting and with major low-angle zones of decollement termed slide planes. Miscellaneous structures. Among the vast number of sedimentary structures that have been observed, many do not fit conveniently into the simple tripartite scheme outlined earlier. These miscellaneous structures include rain prints, salt pseudomorphs, and various vertical dike-like structures of diverse morphology and origin. These include desiccation cracks, syneresis, cracks, sedimentary bodinage, and sand dikes. Rain prints. Rain prints occur within siltstones and claystones, and where such beds are overlain by very fine sandstones. In plan view, rain prints are circular or ovate if due to wind-blown rain. They are typically gregarious and closely spaced. Raised ridges are present around each print. Individual craters range from 2 to 10 mm in diameter. Rain prints are good indicators of subaerial exposure, but are not exclusive to arid climates, though they may have a higher preservation potential in such conditions. Salt pseudomorphs. Salt pseudomorphs occur in similar lithological situations to rain prints. They are typically found where claystones or siltstones are overlain by siltstones or very fine sandstones. Desiccation cracks. A variety of vertical planar structures have been recognized in sediments, and these include shrinkage cracks, sedimentary dikes, and Neptunian dikes. Shrinkage cracks are often recorded in muddy sediments. They are of two types. Desiccation cracks form subaerially, syneresis cracks form subaqueously. Desiccation cracks, also known as sun cracks, are downward tapering cracks in mud which are infilled by sand. In plan view, they are polygonal. Individual cracks are a centimeter or so wide. Polygons are generally about 0.5 meter across. Syneresis cracks. Syneresis cracks are formed in mud by the spontaneous dewatering of clay beneath a body of water. White, 1961, Plummel and Gostin, 1986. They are distinguishable from desiccation cracks because they are infilled by mud similar or only slightly coarser in grade than that in which they grow. Furthermore, syneresis cracks are generally much smaller than desiccation cracks, typically only 1 to 2 millimeter across. Sand dikes. Sand dikes are vertical sheets of sand that have been intruded into muds from sandbeds beneath. Though they are sometimes polygonally arranged, they can be distinguished from desiccation cracks by their tendency to die out upward and by the fact that they are rooted to the parent sandbed below. Sand dikes are intruded as liquefied quicksand into water-saturated mud. Like desiccation cracks, they often show stigmatic compaction effects. Secondary structures. Chemical sedimentary structures. Chemical sedimentary structures are formed by chemical processes such as oxidation reduction, precipitation, evaporation, etc. Cone-in-cone structures. It is a structure commonly found in fibrous calcite and fibrous gypsum sediments. It has the appearance of a series of cones packed the one inside the other. This structure appears to be due to pressure. Stylolites. It is formed by the erosional activity of groundwater. When the carbon dioxide-rich water percolate through the bedding plane of limestone rock, soluble parts are removed and away, and insoluble parts exist there. They appear as an irregular structure, zigzag line of junction between them. This type of structure is called stylolites. Concretionary structures. Concretions consist of round or irregular masses of more resistant rock formed as a result of cement precipitating around a core material, usually a fossil or grain of a different composition. There are two types of concretionary structures. Oolitic structures. Oolites are small, 0.1 to 1 millimeter, concentrically layered, spherical grains composed of primary carbonate materials or replacement phases. Pisolytic structures. Individual size of a concretion is like that of a pea nut. Limestone and bauxite shows both structure. Geode. It is a structure formed by the depositional activity of groundwater. It is a cavity in rocks lined with well-developed crystals of quartz projecting towards the center. Vogue. It is a cavity in a rock, usually with lining of crystalline minerals. The term is used especially of cavities in mineral veins. Crystal casts. Crystal casts are formed when a soluble crystal, that is salt, dissolves in solution, followed by filling of mud or sand in its place. Biogenic sedimentary structures. Biogenic sedimentary structures are features which are formed by biological activity. Stromatolites. These are biogenic laminated structures which have a great variety of growth forms. They develop through the trapping and binding of carbonate particles by a superficial microbial mat or algal mat composed mainly of cyanobacteria, formerly called blue-green algae, and other microbes, and the biochemical precipitation of carbonate. Stromatolites are very common in Precambrian carbonate successions, but they also occur in many Phanerozoic limestones, particularly those of peritidal origin. Stromatolites are finely laminated algal accumulations greater than 10 cm in diameter that result when algae grow upwards, trapping carbonate mud into thin layers. Escape structures. Escape structures are columns, holes, or tubes that cut across bedding and are infilled with sediment after the escape of water or a burrowing organism that had been trapped beneath a newly deposited sediment layer. Reefs. Reefs are domed to elongate, massive to bedded forms built during carbonate deposition by organisms that biogenetically precipitate carbonate materials. Casts and molds. Any depression formed on the bottom of a body of water may become a mold for any sediment that later gets deposited into the depression. The body of sediment that takes on the shape of the mold is referred to as a cast. Tracks. Tracks or footprints are impressions on the surface of a bed of sediment produced by the feet of animals. Examples include dinosaur footprints or bird tracks. In some cases, tracks are found as sole marks on the bottoms of beds where sediment has infilled the tracks and preserved them as casts. Trails. Trails are groove-like impressions on the surface of a bed of sediment produced by an organism which crawls or drags part of its body. Trails may be straight or curved. Burrows and borings. Burrows are excavations made by animals into soft sediment. Burrows may be used by organisms for dwellings or may be produced as a subterranean organism moves through the soil or sediment in search of food. Burrows are commonly filled in by sediment of a different color or texture than the surrounding sediment, and in some cases, the burrows may have an internally laminated backfilling. Burrow fillings may become cemented and hard, weathering out of the rock in rope-like patterns. Borings are holes made by animals into hard material, such as wood, shells, rock, or hard sediment. Borings are usually circular in cross-section. Summary. Sedimentary structures are macroscopic, three-dimensional features of sedimentary rocks, recording processes occurring during deposition or between deposition and lithification. They are probably the most critical means of interpreting sedimentary and post-depositional processes. Their recognition and application are key to defining depositional environments, geological history, and surface processes. Sedimentary structures function as geopetal structures, indicators of original verticality. Directional structures, indicators of current direction and identifiers of the agent of transport. Primary sedimentary structures occur in clastic sediments and are produced by the same processes, currents, etc., that caused deposition. This includes plain bedding and cross bedding. Secondary sedimentary structures are caused by post-depositional processes, including biogenic, chemical, and mechanical disruption of sediment.